A launch vehicle such as this Saturn is subjected to loads, shocks, and vibrations from a number of sources as it ascends through the atmosphere. Among the more important loading sources are the horizontal winds, which are encountered during this portion of flight. Studies have shown that the winds vary considerably, even over small differences of altitude, and at some altitudes, the winds may reach velocities greater than 200 miles per hour. When a vehicle travels at high speed through these winds, it feels them as a series of fluctuating forces or loads of varying frequencies and wavelengths. Such unsteady loading conditions are of great importance in connection with designing the structure of the vehicle. The vehicle responds not in a rigid manner, but as a flexible body, and the vibratory effects can amplify the structural loads to values much greater than for rigid bodies. A coupling between the resonant vibrations within the structure and the control system may also lead to guidance and control problems. To learn more about the detailed nature of the wind structure, a research project was undertaken by the National Aeronautics and Space Administration. Project management was assigned to the Langley Research Center. For many years, the sounding balloon has been employed at various locations throughout the country to obtain measurements of the winds at altitude. The wind profile obtained from a single balloon launching may look like this, or like this. Each point on the plot represents an average wind over an altitude interval of about 2,000 feet. But recent studies have shown that the winds are not nearly so uniform as these balloon data suggest. A plot of winds at the in-between levels may look like this. Notice the small variations not revealed by the balloon data. The cause of these small disturbances is not well understood, but they are important because of their dynamic loading effects on the launch vehicles. To learn more about the true vertical structure of the winds, the project engineers selected a method which would give far more detailed data than the conventional balloon sounding method. Chosen was a method which used a rocket to produce a smoke trail as a continuous wind sensor along a representative rocket flight path. Phototriangulation on the trail permits determination of the wind velocities. The rocket was a standard Nike booster, fitted with a nose cone of special design. The nose cone was filled with a smoke-producing chemical. The project called for firing some 100 of these rockets from Cape Kennedy over a one-year period. The results provided a detailed picture of wind conditions at the Cape for use in launch vehicle design studies, as well as information for studies on the cause of the wind disturbances. Each rocket was launched on an almost vertical path. It accelerates rapidly upward during the burning or thrusting phase of the rocket motor, while the chemical solution is held in the aft portion of the nose cone. The solid fuel propellant burns out at about 6,000 feet. At this point, the rocket experiences a large decelerating force due to air drag, and the chemical shifts forward and starts escaping through the vent to the atmosphere. The particles formed are hygroscopic. Atmospheric water vapor condenses very rapidly on the particles and forms a highly reflective trail. In this manner, a trail extending to a considerable altitude is produced by a small amount of chemical, a feature which has great advantage from the standpoint of payload weight. In the smoke trail wind measurement program, a trail is formed from an altitude of about 6,000 feet to 75,000 feet. The use of a continuous trail of this type as a wind sensor makes possible an accurate determination of wind speeds and directions simultaneously over a large altitude range. Good weather and visibility are, of course, necessary. The data reduction process is based on phototriangulation techniques. Sets of photographs of the trail taken simultaneously from two camera installations are used. The cameras are located 10 to 12 miles from the launch site and form the legs of an approximate right triangle. Simplified, the process works like this. From one pair of simultaneous photographs, determine the coordinates in space of each point in the smoke trail. Do the same for a second pair of photographs, taken a short time, say 30 seconds later. The wind speed and direction at each small increment of altitude can then be determined from the measured drift of the trail. The photographs of the trail are taken by this camera and a second one about 10 miles away. The cameras are synchronized by range timing signals. Target boards like this appear on each photograph, providing reference marks for use in the data reduction stage. The cameras are operated for 5 minutes or more, depending on the persistence of the trail. Precision modified aerial mapping cameras are used to provide high-quality photographs. They incorporate such features as vacuum flattening of the film to minimize distortion. The data reduction is handled jointly by the Langley Research Center and the Marshall Space Flight Center. Film reading is carried out in a humidity-controlled room. A slight distortion in the negative could produce a large error in the results. Analysis corrects for errors caused by such factors as lens and focal plane distortions, film shrinkage or stretching, atmospheric refraction, and variations in film thickness. As the final step, the computer solution is fed into a magnetic tape plotter. It produces plots of the north-south and east-west components of wind velocity against altitude. These results are accurate to about 1 foot per second, compared to about 10 feet per second or more for conventional balloon tracking methods. More important, a point is plotted for about every 75 feet of altitude, compared to 1,000 feet for other commonly used methods. One or more wind profiles are plotted for each launching. The winds are found to vary greatly from day to day, even from hour to hour. No statistical method has yet been found for reducing the individual profiles to a more readily usable form. But even in this form, the data can be used to test the design of a new launch vehicle. The vehicle can be flown by means of a computer through each of the profiles to determine whether the intended design would result in control system difficulties or excessive loads. The data from these tests are available to meteorologists to permit their study of the nature and causes of these wind disturbances. A better understanding of the phenomenon will be of value to both launch vehicle designers and meteorologists.